In this lecture, I will discuss about the DAPT NMR technique. So what is DAPT? So we are doing proton decoupled carbon NMR generally, as we have discussed in the section of carbon NMR. So we are losing the information about the number of proton attached to individual carbon. So DAPT or distortion-less enhancement by polarization transfer is a technique to get the information about the proton attached to carbon. That is, we have CH3 or CH2, CH or quaternary carbon in a molecule. So we can find that how many methyl, how many CH or how many quaternary carbon we have in our molecule. So this helps to interpret the NMR spectra to find the structure of organic molecules. So in a DAP technique it is a double resonance pulse program that transfers polarization from proton to carbon nucleus. The sample is irradiated with a complex sequence of pulses in both the 13C and 1H channels. The result of these pulse sequences is that the 13C signal for the carbon atoms in the molecule will exhibit different phases. Depending on the number of hydrogen attached to each carbon, each type of carbon will behave slightly different depending on the duration of the complex pulse, and this difference can be detected and spectra produced in each experiment can be plotted. Now come to what exactly we observe in DAPT NMR, which is important for us to find the structure of organic molecule. So we run DAPT NMR in 4 stages. First, ordinary broadband decoupled spectrum, as we do generally for carbon NMR. This gives information about the chemical shift of all carbon signal in the molecules, regardless primary, secondary, tertiary or quaternary. So because this is a general carbon NMR, so we will see peaks of all type of carbon there. DAPT 45. It gives the signal only for protonated carbon, means signal for quaternary carbon will be missing here. DAPT 90 only gives signal for CH carbon, means carbon having only one proton attached to them will give signal in DAPT 90. Carbon for CH3 or CH2 or quaternary carbon will be missing in DAPT 90. DAPT 135. It gives CH3 and CH signal positive means above the baseline, and CH2 signal appear as negative signal means below this baseline. There is no signal appears for quaternary carbon. So based on these 4 stages, we can find that which signal comes from CH3 in our spectrum, which signal is coming from quaternary carbon, which signal is coming from CH2, and which signal is coming from CH carbon. So let's take the example of isopentyl acetate. So this has 6 type of carbon. So first take the general carbon NMR that's shown here, which is the proton decoupled carbon NMR. So you can see the signal for each type of carbon here. Means total we have 6 signal in this carbon NMR. But now we are taking DAPT 45. Means DAPT 45 shows only peaks for CH, CH3 and CH2 carbons. No peaks will appear for quaternary carbon. So you can see peaks for carbon number 6 goes miss here. Means it's not showing any peaks for quaternary carbon. So this shows that carbon number 6 is quaternary carbon. As you can see, this is quaternary carbon. Now take the DAPT 90, which shows only peak for CH carbon. So this shows we have only one CH carbon in our molecules. The all peak goes miss here. So this peaks belongs to carbon number 2 or this one. So you can see this 2 is only the CH containing carbon in our molecule. That's why we are getting only one peak in DAPT 90. Now DAPT 135 gives peak for CH3 and CH3 above the baseline and for CH2 below the baseline. So you can see this peaks belongs to CH2, which is belongs to carbon number 3, and this peaks also belongs to CH2 because this is on the below the baseline. So this is for carbon number 4, and these all peaks belongs to CH3 and CH carbon. We already know that this peaks for CH and these 2 peak will be for CH3 because we already have seen this peak in DAPT 90. That gives only peak for CS. So by doing these four stages, we are able to find that which carbon is quaternary, which carbon is connected to 3 proton, which is to 2 proton, and which is only connected to 1 proton. So this information help us to find the structure of organic molecule. Now take the another example of this molecule. So this molecule has plane of symmetry. So half part will be equivalent to the other half part. So finally this molecule will show only 1, 2, 3, 4, 5, 6 signal in carbon NMR. So just let's take the general carbon NMR. So here we are getting 1, 2, 3, 4, 5, 6 peak. 2 peaks in the saturated carbon region and 3 peak in aromatic region, 1 peak in carbonyl region. Now let's take the depth 45. So one peak goes miss here, that's in carbonyl region. So this shows that this peak belongs to quaternary carbon. Now take depth 90, which shows peak only for CH carbons. So here we are getting only 2 peaks. So this shows we have only 2 carbons attached to 1 proton. Means only 2 CH carbons available in our molecules. Now means these two peaks belongs to CH3 or CH2, but we are not sure which is CH3 and which is CH2. Now let's take the depth 135, which shows one peak below the baseline and one peak above the baseline. As we know, above the baseline will be either CH or CH3 and below the baseline will be CH2 in depth. So this peaks belongs to CH2 carbon and this peaks belongs to CH3 carbon. So again we are able to find that which is peaks belongs to quaternary carbon, which peaks belongs to CH2 carbon, which peaks belongs to CH3 carbon or CH carbon. So in this way, we are finding the structure of organic molecules and we are getting the information about the protons attached to carbons, which we are missing in proton decoupled carbon NMR. And thank you very much. Have a very nice day.